My name is Tayyab Adnan. I'm a graduate student at Clarkson University, and my research is guided by Professor Robert Thomas. And today my presentation is on alkali-silica reactivity of Belitic calcium sulfoaluminate cement concrete. So Belitic calcium sulfoaluminate cement, simply known as BCSA, is an eco-friendly and sustainable cement. It's used as a rapid repair material. But in the recent years, it's been researched upon as an alternative to Portland cement in structural concrete. But for that, we need to have detailed knowledge of the strength and durability of this concrete. So my presentation today is related to that durability part, where specifically I'll be discussing on alkali-silica reaction. So the question that needs to be answered is BCSA resistant to ASR? So for that, first thing that we need to look in, like we have two things that needs to be looked upon. So one is like the initial thing, that is alkali content, and the other is alkali recycling. So for alkali content, what is needed is basically the cement has to have less alkali. So it supplies less alkali for the reaction, and you hope that that it has less alkali, so less ASR in the concrete. The table on the right has a comparison where you have BCSA and Portland cement, the oxide composition. And what we need to look into is the total alkali content. For BCSA, it's less compared to the typical Portland cement composition. So which is a good start. But the other thing that we need to look upon is, do we have alkali recycling? So for that, what needs to be checked is, so calcium hydroxide can still make the reaction continue even though if you have less alkali content. So since BCSA has belite in it, it's important that the performance for ASR is checked. So that's the objective of the research. And if you can state the objective, so it's like the first thing is to evaluate what ASR for BCSA cement using the accelerator test ASTM C1567 and the long-term test C1293. And the next is to validate the results of the accelerator test for use with BCSA cement. And the third is to validate the results of the long-term test using petrographic analysis. So I've used two cements, one is BCSA, and I've also used Portland cement specimens for comparison. And the aggregates I'm using are is the natural non-reactive natural sand, which is the control aggregate, and I've used reactive Spratt siliceous limestone, which is known to be ASR reactive. So the table on the right shows the test methods and the exposure period. So for the accelerated test, the exposure period is 14 days. And for the long-term test, the exposure period is 2 years. I'd like to add that the mortar mixes that I've used is the same for both the test methods. So I've used the same mortar mix, but in different test environments for the study. So here are the results of the expansion test. So let's start with the accelerated test, which is on the left. So the plot has a comparison of the exposure period and the expansion. By expansion, I mean the length change as a result of the test. So for the accelerated test, you have an ASTM limit, which is like 1000 microstrains. So the mixes which the specimens which cross the mark in the test period are considered to be ASR reactive. So let's start with the non-reactive mixes, which is Portland cement and BCSA. So here NRA is non-reactive aggregate. So we can see that the performance is good in terms of they qualify the test. They are not ASR reactive. So it's a kind of expected thing because they don't have reactive silica to promote to continue to have ASR reaction there. So sorry, ASR. And if we see the performance of the Spratt aggregates, which are known to be reactive, both Portland cement and BCSA show high expansion. One thing that is a bit surprising here is the test shows that the BCSA is having even more expansion than the Portland cement itself. So if we just compare the performance, like the results with the the long-term test ASTM C1293, which again has a limit. The limit here is 400 microstrain. The thing is, like when we see here, the performance is contradictory, where you have Portland cement, it's Spratt showing the highest expansion, And this performance of BCSA Spratt is actually like significantly lower, like less expansion here. So compared to the Portland cement with Spratt, even though you can say that it can like it still fails the test in terms of its performance. At 500 days, it does cross the limit. But the thing that we can compare here is the performance, like in terms of expansion, is less than what we see in Portland cement with reactive aggregates. So that's again a good sign. If we check the performance again for the non-reactive aggregates, Portland cement with seems to perform the best. But while BCSA does have good, like it does fall within the limit, but at 500 days again it crosses the limit, but the expansion is not too high, and this cannot be completely stated as something with ASR. It can be something with the reaction product that needs to be looked upon. So we can't just like state that it is ASR just because it has crossed the limit. But again, for this to confirm the results of this test, I have done petrographic analysis. So the petrographic analysis is done on the long-term test specimens to find ASR cracks and so what I've done in here in petrographic analysis is that I've used SEM, and the image here is for Portland cement with non-reactive aggregates. So what you can see here is the cracks that here in this image are mostly concentrated in the paste region, and it's not something a typical ASR crack through the aggregate. So the cracks here can be a result of the desiccation from the specimen preparation process and not something related to ASR. Here you see an image of BCSA cement specimens with non-reactive aggregates. Again, majority of the cracks are focused mostly on in the paste region, and even though you can say like there are some cracks through the aggregate, but it's mostly concentrated towards the periphery and not a typical ASR crack through the aggregate. Again, what we can say is like it's something as a result of the desiccation from the drying process and not a clear indicator of like ASR. So here we see Portland cement with reactive aggregates. So here we can see a proper ASR crack through the aggregate. So here in terms of just the cracking, it is consistent with what we expect for ASR. And for BCSA cement with reactive aggregates also, you can see that the cracks are through the aggregate and a typical ASR crack. But even though it cracks here, you can say that BCSA cement again shows ASR cracks. But what I can say is based on the comparison like with the long-term test, even though it cracks, the expansion is not too high compared to the performance of Portland cement with reactive aggregates. So I'll be doing further analysis. So this is an image of what I'm doing. Like currently, it's I'm using EDS and a mapping technique to get the composition because I want to find ASR gel and get more information on the chemical composition of the gel itself. So what you see here is Portland cement with reactive aggregates and the images here. So let's start with calcium. So what we expect is we have a Spratt siliceous limestone. So we do have traces of like you can see calcium there. It's pink, and all the paste also has calcium. So it's there visible in the image, and the silica on the right is visible because we use Spratt siliceous limestone, so we tend to expect to have silica there. And aluminum, because the cement has aluminum, so we see some traces of that. But what I would like to see, like the most interesting thing would be to see traces of sodium or potassium. So here it's like uniformly distributed. The potassium that you see in the image, which is not an indicative that you have traces of potassium. You should have some maybe in the cracked regions or some spots. There's some selective spots where if you find traces, that means we can do more analysis and see the chemical composition. So that may be an indicator of an ASR gel. So that is something I'll be doing. So it's an ongoing research, and that will be something which will be continued in the future. So based on these results, I can conclude that the accelerated test results don't fully align with the results of the long-term test. So if some concrete mix is just judged on the results of the accelerated test, that may not be an ideal representation of how the concrete will perform at site. So we need further results again to validate the results of the accelerated test and even do further analysis. So based on, okay, also BCSA is not fully immune to ASR, but it does show limited expansion in the long-term test, which is a good sign. So if you don't have excessive expansion, that means you have less cracking, and that's like the comparatively it may have a less structural deterioration if the process is it continues. Then and the third thing is the cracks that are formed in the Spratt specimens are consistent with ASR. Just based on the cracking itself, we can say that Portland cement and BCSA with Spratt specimens show ASR cracking. So and further and the last thing that I would like to conclude is like I have to do further petrographic analysis, so that will be done in the future to find contents of the ASR gel. And I would like to thank Professor Robert Thomas for all his guidance in the research, and I would also like to thank CTS Cement for sponsoring this research. And finally, I would like to thank ACI for giving me this opportunity to present my work here. Thank you.